from that. So minus 42 gives us a test statistic of 10.1697. So that's the magnitude. This is the magnitude of the differences in the ranks. Okay. So what we need to do now is this: is that we need to well, we've just done step 1, 2, and 3, our test statistic. Step 4 is our critical values. Okay, so step 4 is to calculate the critical values. Okay, for this particular test statistic. And to calculate the critical values, we need a set of tables. We need to know our alpha, which is 0.05, and we need to know how many groups we have, which is k, in this case is equal to 3. There's 3 groups. This is how many groups we have. And then we need to go to a set of tables that allows us to look up for the Kruskal-Wallis H-Test. Okay? Now I've got a set of tables here that I'm going to use. And I've actually taken these tables. I'm using these tables out of a great text in relation to non-parametric statistics, which is by Corder and Foreman, and it's a step-by-step approach. But I'm just going to look at these tables here. And what we need for these tables is we need to know the size of the first sample, the second sample, and the third sample, which is 4, 4, 5, and k is equal to 3, the number of groups, and our alpha level is 0.05. So we're looking for 4, 4, 5. So I'm looking for 4, 4, 5. 4, 4, 5. Would you believe it? It doesn't go up to 4, 4, 5 for some strange reason. Yeah, it stops at 4, 4, 4. But look, let's just actually take this as an example. Let's assume that this was a 5. Look, I'm introducing a little bit of error here. Okay, you can see the differences. Yeah, you can see the differences in relation to when these grow up here. When these go through the 4, 4, 1, 4, 4, 2, 4, 4, 3, 4, 4, 4. Okay, so it goes from 4.9, 5.4, 5.5, 5.6. Okay, so it's probably in around 5.7. It's probably in around 5.7, 5.79. Yeah, for a 4, 4, 5 scenario. I should have really looked at these tables to make sure that we had the right amount. But I mean, the key point here is this: is that you need to know the first sample size N1, the second sample size N2, and the third sample size, which I'm looking for is 4, 4, should be a 5, but I have a 4 here. But look, you can see under the alpha is equal to 0.05, there's not really much of a difference between when the third sample is a 4 and a 3. Very small difference. It's 0.1 of a difference, yeah, in them. So I'm just going to assume, and then between a 3 and a 2 it's 0.1 as well. So I'm going to assume it's a 0.1. So this is probably let's say it's 5.7, yeah, 5.75, yeah, 5.76. So our critical value is equal to 5.7 approximately. Okay, approximately. So I'm introducing a little bit of error here, okay, because I'm missing that particular value on my tables. Should have really looked ahead on in this particular instance. But anyway, our decision criteria is very simple. If H, the test statistic, is bigger than the critical value, we reject. Okay, otherwise we fail to reject. Okay, and in this case here, clearly we have that H, which is 10.1697. It is bigger than 5.7, which is equal to our C, and as such we reject H0 in favor of HA, and infer, so now we can make our inference because we rejected, and infer that at least one pairing of groups have different ranks, have different ranks. Okay, so there's a difference between them, if that makes sense. Okay, and actually when you think about it, the difference that we've just observed has to be between the smallest and the largest set of ranks. So it has to be between group B and group C. It could be between group A and group C also, and also between group A and group B. But we'd really have to follow this up with a post hoc test, and the most appropriate probably test here would probably just to do a Mann-Whitney between two groups to see where the differences actually reside. Okay guys, once again this is Jonathan Lambert with the Mathematics Development and Support Service at the National College of Ireland, and in this short video, another video in our series of videos dealing with non-parametric statistics, I concentrated on the non-parametric version of the ANOVA, which is called the Kruskal-Wallis H-Test. It's an independent samples test, but more importantly this video is a concentration when there's no ties in the data. The follow-up video after this will be where we take into consideration ties, and we have to modify this formula with a correction factor. We actually divide the H by the correction factor, depending on how many groups there are that have ties in them. Okay. So once again, guys, thanks for watching. I hope that this video was intuitive, and more importantly, I actually hope that was helpful for you. Thank you. Bye bye.